So now I leave the floor to Dr. Garcia, which will talk about LCA and Technoeconomic Assessment of the Cosmos technology. Dr. Garcia, the floor is yours.
Thank you. I will share my screen.
Yep.
Okay. Can you see my slides in the presentation mode?
Yes, I can.
Okay. Perfect.
Please,
okay,
go ahead.
Thank you. So, hello everyone. My name is Guillermo Garcia. I'm a research associate in the University of Seville. I assess the environmental impact of industrial processes. And today I'm going to give you an overview of my work on LCA and DA of the Cosmos technology. So today I'm going to cover the following. I will firstly introduce the LCA and DA methodologies. I will show you the main findings of a literature review we undertook of LCA studies of Ccu Products. Then I will show you the results of a catalyst screening according to their environmental impacts. I will then describe the first stages of the full LCA and DA that we are undertaking for Cosmos. And in the end, I will present the main conclusions of this work so far. Okay, so, well, we have seen that there is a growing interest in CCU, and consequently, there is a demand on studies of their environmental and economic performance. However, it's quite difficult to analyze these aspects for CCU technologies, as often they are still at lab scale. So in these cases, it is very important to use systematic methodologies. So to analyze environmental consequences of decisions, we can use the Lifecycle Assessment, LCA, methodology. To analyze economic consequences of decisions, we can use the Technoeconomic methodology, DEA. And they both can be used to analyze effects of implementing CCU solutions and also compare them with current scenarios. So therefore, LCA and DEA can help us answer the following questions. What are the environmental and economic consequences of CCU? Can CCU reduce carbon dioxide emissions and be economically profitable? Firstly, what exactly is LCA? Lifecycle assessment is a methodology to assess the environmental impacts of a product, a service, a process, a company, etc. And there are two particular aspects of the LCA methodology. It should consider all life cycle stages of whatever is being analyzed, so including raw material extraction, manufacturing, transport, use, disposal, etc. And it should also consider a wide range of environmental impact categories. For example, global warming, resource depletion, toxicity, acidification, land use, etc. So LCA is nowadays a popular and widely used methodology. And because of this, it has been standardized by the International Standard Organization, specifically in ISO 14040 and ISO 14044. So these two standards explain how to undertake an LCA study. This LCA study should include always 4 major phases, which is the definition of the goal and scope, the inventory analysis, the impact assessment, and the interpretation. And we conducted an exhaustive review of the literature to analyze published LCAs of these following products produced via CCU: methanol, methane, DME, DMC, propane, and propene. And we tried answering these questions here. What are the most promising products that could be produced from CO2? What are the potential environmental impacts and/or benefits of producing these products from CO2 in comparison with traditional methods? And what is the level of application of the LCA methodology to study CCU? So the main finding is that there are good opportunities to produce valuable products from CCU. However, there are a few aspects to consider. Firstly, we need to use green hydrogen to make sure that the environmental impacts of the CCU route are lower than those of the conventional route. So we should produce this hydrogen via water electrolysis using renewable electricity. Also, CO2 capture, separation, purification, and transport creates significant environmental impacts, particularly the capture of CO2, and this has sometimes been excluded in LCA studies. We need full LCAs to quantify the environmental impacts of these technologies, and we need to consider a wide range of environmental impact categories, not only global warming or climate change, and also as many life cycle stages as possible. We also found that historically, few LCA studies of CCU systems have been undertaken, and this is because CCU technologies are rather new. However, the number of these studies is now rapidly increasing. Also, there are some discrepancies between the different studies, even if they analyze the same product produced by the same route. And the main reason for this is the different methodological choices and assumptions made. For example, the supply of feedstocks, definition of the system boundaries, and the way to allocate products and co-products. And as opposed to what I recommended in the previous slide, most studies focus on climate change or global warming only. So we feel that there is a need for a common framework for LCA of CCU. So for that, we are using the guidelines for LCA and DA of CCU, and I will talk about them a bit later. You can find more information about this latest review analysis in our paper Analytical Review of Lifecycle Environmental Impacts of Carbon Capture and Utilization Technologies. So this was published in Chem in the last month, and you can download it for free at this link. Now, let me briefly introduce you to the COSMOS project. This is an international collaboration between a number of universities and industries, and with the aim of taking the emitted carbon dioxide and transform it into propane and propene in one reactor. You may have heard about the Richard's presentation in the morning. He introduced the project, and there is another presentation looking into this in more detail in the parallel session. So to transform CO2 into propane and propene in one single step, we need catalysts. And these three are the shortlisted catalysts that we identified in the project. And as you can see, each catalyst is actually formed of a pair of catalysts. Okay. So we did a preliminary environmental impact study of these catalysts. We compared the environmental impact of their production following a cradle-to-gate approach. So this includes the extraction of the raw materials and the production of the catalysts. Here, at the moment, we are still excluding the use of the catalysts and the end of life of the catalysts. So to make a fair comparison between the three catalysts, you have to choose the same functional unit for the three of them. So we initially set this as 1 gram of catalyst produced. So to undertake this study, we used Gabi. Gabi is an LCA software that has access to a number of databases and can calculate the environmental impact of processes. So here you can see a few screenshots from the models that we built for the different catalysts. So to build a robust model, we need to access datasets relating to the upstream operations, like, for example, the mining of a metal, or also background data like the grid mix information for a specific country. So these databases provide a lot of information on inputs and outputs and detailed emissions that can be used to calculate the different impacts. And here we can see some of the preliminary results, and the catalyst with the highest global warming potential by far was the one with palladium. So the impact from the palladium catalyst was coming from the palladium content itself, and this is an upstream impact from the purification process, which is used to produce one of the intermediate palladium products. For the other catalysts, the largest impact is also coming from the metallic component. And we also looked at other environmental impact categories, not just global warming potential, and the results were very similar. The bars represent the relative impact of the catalysts, and the palladium catalyst with the blue bars is again the worst one when looking at other environmental impact categories. We did two sensitivity analyses to test our results. We included the Cosmos reaction yield and two different preparation methods of the catalyst. So in the previous slides, we had not included the reaction yield, as we were just comparing the catalyst per gram of catalyst produced, not per gram of the final product produced. Actually, the reaction yield is higher for the palladium catalyst, so we wanted to check if an increased yield would overcome the higher environmental impact. And we also checked the catalyst preparation method, as there are two methods to prepare the palladium catalyst, the conventional impregnation and the colloid impregnation. So with this data that we used, we have seen that the relative impact of the palladium catalyst was reduced in both cases, but still it remains significantly higher than for the other ones. And I think that this proves why it's important to do an LCA, because sometimes just looking at the reaction or the reaction yield, you may expect the impacts to look a certain way, but when you include the upstream impacts, the results can be different. And anyway, we'll do a full LCA of the Cosmos process in the next months, and we'll then get much more data. So now let's talk about Technoeconomic Assessment. TEA is a methodology to analyze the technical and economic performance of a process, product, or service. And you may have heard about lifecycle costing, LCC, which is very similar to LCA, but looking at economic costs. TEA considers cost, but also revenue and technical criteria. So it's not the same as LCC. And as with LCA, TEA is an assessment methodology. Once you have completed your TEA study, you will have to use the output data to make a decision. So TEA can be undertaken following a similar methodology than that of LCA. So in this way, the main phases are the goal, to identify the specific aim of the study, scope, to define the system boundary, inventory, to collect the relevant foreground and the background data.
3 minutes.
Yes. Okay, I'll try to be quick. Calculation to produce results, interpretation, and report. So for Cosmos, we have to complete a lifecycle assessment and techno-economic assessment. And both methodologies follow a lifecycle approach, so these studies will have to be aligned. And they will have the same scope and certain elements of the goal. So the main goal is to assess whether the use of carbon-intensive gases from the steel industry and the petrochemical refinery to produce propane and propene would have an economic and/or environmental benefit when compared to the conventional production of these products. We'll be doing a gate-to-gate study, and we will be comparing different scenarios. So in this case, the functional unit will be the production of 1 kilogram of propene. And this is the simplified Cosmos process. As you can see, we use a gas emitted by the industry, reacted with hydrogen, and then after a number of processes, get the C3 products and also some byproducts. So we have two different baseline scenarios, which is the status quo of the companies we are working with and that produce these gases that we are using as input for our process. So these companies are Tata Steel and Tupras. So we'll go very quickly over the different scenarios. So for scenario 1, the input is the blast furnace gas that comes from the steelworks. the gas is currently sent off-site for electricity generation, and this electricity avoids the generation of electricity from the grid mix, so this receives an equivalent environmental credit or benefit. To make the scenarios comparable, we had to expand the system boundaries to include the propane production, so we scale everything to produce 1 kilogram of propane. And obviously, there will be other resources and also other emissions that we'll include in our study. In scenario 2, the blast furnace gas is still the input of the system, but now this goes into the Cosmos process that produces propane, also produces propylene, which in this case displaces the conventional production of propylene, and this also receives an environmental credit. So scenario 3 is the reference case for Tupras. Here we're using the PSA tail gas, which is used for heating purposes. And again, we have to include the propane production in the system boundaries, so we can scale everything up to the production of 1 kilogram of propane. And the Cosmos scenario for Tupras, in which the PSA tail gas is no longer sent for heating purposes, but it is instead used in the Cosmos reaction. So the Cosmos reaction will produce propane and also other products, which displays the conventional production of those products. And also we have to include here the additional heat that we need to compensate from the scenario 3. So if you'd like to know, yes? Okay, continue. So we'd like to know more about this, particularly about how to conduct an LCA and or TEA of the Ccu technologies. I recommend you reading the guidelines I mentioned before. We developed them here in the University of Sheffield with the help of several industrial partners. And you can download them here for free at this link. So just to conclude, we can use LCA to calculate the environmental impacts throughout a product or a process lifetime. We can use TEA to analyze the technical and we can use TEA to analyze the technical and economic performance of a process or product, and both methodologies can be used to support decisions based on environmental and techno-economic performance. With the LCA, we are also identifying the main bottlenecks in the Cosmos process, and we also analyzed the potential environmental impacts of the different catalyst choices. And at the moment, we are looking into the full LCA and TEA of the Cosmos process. So I would like to acknowledge the contribution of my colleagues in the University of Sheffield and Tata Steel, and I will conclude here. Thank you very much for your attention.
Thank you very much, Guillermo. Thank you for this very nice presentation and respecting the timing. I don't know if there is any question from the audience. While people write the question in the chat, I have a question for you, which is the typical issue when running LCA and Technoeconomic Assessment. What if the outcome of the two analyses are contradictory? Okay. So the palladium catalyst, for example, for your case, is the most interesting one from economic point of view, but in the end, from environmental point of view, it's the worst case. How can you compare them?
Yeah, that's something that happens quite often in this kind of studies, and it's a real problem. There is not a clear answer. In the end, what we will try to do is aggregate all the results. So the environmental results, economic results, and also social results that I didn't include in the presentation, and produce kind of a generic singular score, generic metric, in which it will be much more easy to compare different scenarios or production processes, for example, the Cosmos and conventional methods. But obviously, the aggregation of these very different results, environmental, economic, and social, is complicated, and you can argue if you are doing this in a fair way.
It's arbitrary.
Sorry?
It's arbitrary if you do such a mix of things. So the parameters of the weights of the different aspects can be selected arbitrarily.
That's the problem. So you have to report the methodology used, explain very carefully how you did it. But obviously there might be some disagreements. So in the end, you have to provide environmental, economic, and social results, and the decision maker will make their own choice. But we have seen in the LCA methodology, for example, there is normalization, grouping, weighting, and in the end, single score. So these are steps that are now more and more commonly used in spite of the disadvantages that you just mentioned.
Okay, thank you very much. A quick question from the chat. What is your expectation with respect to how important can be the contribution of the catalyst manufacturer to the overall environmental impact of the process?
So I think it's a bit early to give an answer for that. So we are undertaking the full LCA at the moment. We already analyzed how is the environmental impact of producing different catalysts or different pairs of catalysts. We don't know yet how much is going to be the contribution of the production of those catalysts in the overall Cosmos process. So we need more data, and we are in the initial stages of that. We expect that it shouldn't be too high because the catalyst can be reused for some time. So we are talking about large-scale projects, so we expect it shouldn't be too high, but we don't know yet.
Okay, thank you very much for your presentation and for answering the questions. Now we can move to the next presenter, which is, I don't know if Dr. Matras or Dr. Mitchell, who will talk about how can public policy and business model innovation be developed to address challenges of CCUS and realize the opportunity.
Thank you very much. It's Antonia speaking. Can I just check if you can see my screen?
Yes. Welcome, Antonia.
Perfect. Thank you very much. So I'm Antonia, and I work for a company called Engelmann Energy. So we're a low carbon energy consultancy specializing in technical and strategic advice for various public and private sector clients across the whole energy system. And myself and Amelia, who'll be joining me in presenting, work in our CCUS and industrial decarbonisation space. So I've done a lot of work around CCUS from both a technical and a policy perspective, and we'll be sharing with you today some thinking on the business model and public policy support needs for industrial carbon capture as well as CO2 utilisation as well. So first of all, we're speaking partially as part of the C4U project, which some of you will be familiar with, which is a Horizon 2020 project around advanced carbon capture for the steel industries in the North Sea.
Can you go to screen mode, please?
Sorry?
Can you go to full screen mode?
Mm-hmm, yeah. I could go to full screen mode. Is that better?
Yeah, thank you.
Yeah, there you go. So as part of the C4U project, Engelmann Energy are working with Radboud University on basically a part of the project around public policy and business models. So what we're aiming to do for this is to understand the risks and barriers to CCS, including those for the stakeholders in the North Sea Port cluster, and then to create a short list of recommended CCUS business models to help CCUS integration into that North Sea Port cluster and support its deployment financially, as well as constructing an effective narrative for CCUS to contribute to societal readiness and generate public support. So going on for that, the first question really that underpins this presentation is why are policies and business models needed? So obviously the CCUS value chain is complex, and the different parties within the chain have different financial needs and must bear kind of specific risks. So the private sector can't yet justify the large expenditure of some of these aspects or bear the full risk of the CCS chain. So policy and government support is needed in various ways. So business models are needed to incentivize CCS deployment for each of these elements in the chain, both financially and addressing those risks. So for example, for the industrial emitters applying carbon capture, it's a large capital expenditure, and unless they can guarantee revenues, they may no longer be competitive with their kind of international competition without carbon capture fitted. So business models are needed to address that challenge and prevent carbon leakage. But also the business model must also be able to address other needs of the rest of the CCUS chain. So a transport operator needs certainty of CO2 volumes and their transport fees to create a business case, and government and society needs to ensure that we decarbonise at the lowest cost and we minimise the cost as well as the environmental impact. And then finally, CO2 utilisation, which Amelia will discuss more separately, needs a regulatory framework for CO2 accounting, as Guillermo mentioned, and verification of those climate benefits. And we need development of end-use markets and likely financial support for those markets as well. So that mostly sets the scene for what I'm trying to do. So now we'll share with you, I guess, some early findings of our C4U project based on risks and challenges. So for the successful business model, you need to understand the risks that you're trying to mitigate, those risks associated with the technology, so that the model can be effective in reducing those and allocating them appropriately. And it's important to learn from previous project success factors and failures shown on kind of this table on the left, such as management of cross-chain liabilities and effective coordination of timescales. So the right-hand table is a summary of the risks that we've pulled out from technical ones, so those associated with, for example, the equipment and the integration of a capture plant into an industrial facility, to economic and market risks. Typically, those are kind of price uncertainty risks, and finally cross-chain risks. So I won't go through all of these. Many of the technical ones are well understood and have been addressed by some of the early CCUS projects, but the economic risks are still prevalent with factors such as uncertainty over cost for capture energy requirements, or the significant CO2 price uncertainty under markets such as the EU ETS market, making projects more difficult to invest in without strong and certain revenue streams. So that's what we're trying to support here. So what I'll do now is I'll use a project that we've completed on business models for industrial carbon capture to give an example of how business models can be thought about and how we can try to develop the best business model for a particular arrangement. So a business model can be characterized into four components: the revenue model, the funding source, so where does the money actually come from, the risk management practices that are needed, and then the capital and ownership structure. And this slide really outlines some of the potential options under each of those business model elements. But within each of those elements, actually a combination of options can be used. So for example, in the revenue model, there could be a main revenue model, such as a contract for difference type mechanism, which creates an overarching incentive, but you may also have a supporting mechanism as well. And I'll explain a bit more about that later. The funding source is closely linked. So really, where does the money come from? Are you getting it from the taxpayers or the consumers of the product that you're making, or some tax or obligation on other emitters? And finally, risk management is actually one of the most important aspects here for CCUS at this stage of CCUS development. And the mitigation options and risk allocation will largely depend on the revenue model and the capital funding model that you choose. So in this study, once we brought together some of these elements into a set of feasible business models, we tried to assess those models on how likely they were to be successful and their strengths and weaknesses against a set of criteria, which are outlined on the right-hand side here. So, for example, the criteria that make the model acceptable to industrial sites are things like, can the model enable access to capital financing? Does it have a strong enough revenue incentive? And can it protect an industrial site from risks such as CO2 price uncertainty? Whereas for government or the public sector, the main criteria was around ensuring the model minimized the cost to the taxpayer and promotes cost and CO2 reductions, as well as being kind of feasible for the public sector to implement and to administer. So just as one example of a business model for industrial carbon capture, this is a model called the contract for difference, which is used already in the UK power market. And this is being looked at as implementing for industrial sites in the UK, as well as actually some other countries such as the Netherlands, a similar concept. So how this works is the emitter is paid the difference between an agreed CO2 which is basically the subsidy that would be needed to cover the additional costs of applying CO2 capture to their site, the difference between that cost and the prevailing CO2 market price. So for example, this could be the EU ETS value if the emitter is included in the EU ETS. So for early projects, the strike price may need to be quite high because there's more risks, more uncertainty, and so a stronger incentive is needed. So the chart down here kind of shows a basic illustration of how that works. You've got your production costs, then your additional capture costs, the revenue that the site receives by being able to sell its EU ETS allowances, and then the subsidy that's needed to make up the difference. And the assumption is that essentially the value of your products that you're selling increase over time as the rest of the market also decarbonizes and bears additional costs of decarbonization. So what we've done here is we've brought together that revenue model, which is a fixed basically contract on your strike price for the whole duration of the project. Some risk mitigation options such as loan guarantees on capital, so the public sector guaranteeing those to reduce essentially the financing costs. The funding source, which in this case would most likely be general taxation, and then your capital options. And on the right hand side here, you can then see some scores where green shows that the model performs well on that criteria, and kind of orange means that it struggles. So for example, this model struggles to pass those costs onto the consumers of industrial products. So that's just an example. This slide I won't go over it in detail, but it's the outcomes of our assessment for a number of different business models. So this is the one we discussed, the contract for difference, and then there's this number of kind of other mechanisms that could be used in other countries to incentivize. So for example, tax credits are used in the US at the moment, and these radar plots at the bottom show the strengths and weaknesses of each of the models on each of the criteria that I mentioned. And so just to sum up this part of the presentation before I hand over to Amelia. So really the key challenge for industrial carbon capture is providing the revenue level and certainty to incentivize industry to decarbonize and unlock capital whilst protecting industrial organizations from carbon intensive competition, for example, from China or other areas with less stringent climate targets. There are a number of available mechanisms to support industrial carbon capture as well as the full CCUS chain, which need to balance the private and public sector requirements, and we can take learnings from previous projects on the financial structure used there. And each of the revenue models requires support from a suite of risk management instruments to ensure that the risks are addressed where possible, particularly the earlier projects. So for the full CCUS chain, as clusters grow, it may be able to transition to an unsubsidized end state, but that assumes we have global action on climate, and kind of all industrial products or power products need to become low carbon over time, or a border adjustment. CCUS requires a business model for the other aspects of the chain, so the CO2 transport and storage as well, and the integration of these business models is key. And the Netherlands has implemented a mechanism as part of SDE++, which is quite similar to a CFD, which may well form part of the North Sea port kind of business model and business case for each aspect of the chain. So we'll be exploring that in more detail as we work with the C4U project. So now I'll hand over to Amelia to discuss CCU specific policy requirements with you.
Thanks, Antonia.
Amelia, 5 minutes.
Oh, okay. So you've just heard a bit about business models and support mechanisms from the perspective of CO2 capture. So now I'm going to talk a bit about the perspective of utilising CO2. So this could be used as a revenue stream in a business model. However, in order to generate revenue from CCU products, you need to be able to sell them to the market, and the market needs to be willing to buy them. So I'm going to talk a bit about the challenges for CCU products trying to penetrate existing markets, and how interventions such as public policy support can enable competitiveness and drive market uptake. So next slide. So what are the challenges? Firstly, a product needs to demonstrate its suitability to an application, and for investor and market confidence, its ability to be produced consistently at scale. Challenges here are large upfront capital costs, prescriptive style standards or potentially lengthy and expensive testing processes that prevent approval, as well as some markets being generally conservative. So interventions, therefore, to enable CCU products at this stage are the provision of funding, the facilitation of testing and approvals processes, and the updating of standards to be performance-based or to include CCU products. Next slide. Yeah. Secondly, the product needs to be able to have people that are willing to purchase it, be that company procurers, governments, or individual consumers. The challenges here relate to conveying the benefits of CCU products. In particular, product procurers may not engage with their emissions, especially Scope 3 emissions. They may not understand lifecycle assessments, and even in cases where there are carbon pricing mechanisms, it may not be clear how cost benefits could be realised through carbon accounting. So enabling enabling interventions could be increasing awareness and clarifying carbon accounting for CCU. Another intervention is the use of mandates or standards to increase demand and provide confidence in the existence of future demand. Another way to drive market uptake is to just be cost competitive. Easier said than done. Some routes are able to do this already, however, for example, CO2 to building materials. However, in many cases, CCU products carry significant cost premiums. Markets are unable to justify this. Therefore, interventions can act to lower external costs, or they can act to level the playing field through product pricing or subsidies. Okay, next slide. So that's an overview of some challenges. And here I've summarized the enabling interventions. So we have research and demonstration funding, kind of low emission fuel standards, product procurement guidelines, so mandates and obligations to increase demand there. You've got pricing mechanisms, and you've also got things such as certifications, monitoring and reporting, as well as facilitating testing of products and getting them into the market. For example, the US clearinghouse for sustainable aviation fuels. As we're running low on time, I think we'll skip to the next one. So it's important to consider that barriers, drivers and enablers can vary regionally. And some key factors to consider when looking at CCU products are the policy and regulatory support in the region, the cost and availability of renewable electricity, which is particularly important for routes involving hydrogen generation, and the availability of fossil resources, whether the region is an importer or exporter, and how this impacts the regional goals. For example, CCU for synthetic fuels may be more favourable in regions with low-cost renewables, strong support such as sustainable fuel obligations, for example, the blending targets for aviation fuels in Norway, and limited or costly counterfactual fuel availability, perhaps due to limited fossil reserves. Okay, I think that's it then. So any questions?
Thank you very much. So if you have any questions from the audience, please type in. In the meanwhile, I have a question for Antonia. If you go back to the results where you have the spider graph. Mm-hmm. Okay, exactly this one. I mean, I'm not that kind of expert, but can you guide me in understand, according to this graph, which can be the most suitable solution, or what should I get from this graph, considering different approaches, please?
Yes, sure. So broadly what this represents is it shows the strengths of each model. And so where the line is further out, the model performs better on that criteria. So this spider plot that I'm pointing at is the CFD on the top left. And it shows that the CFD model can provide a strong revenue incentive, so it does well on this, and it can protect organizations from kind of lower cost international competition. And
but to compare the FDC with the cost plus, where it has all the aspects but one maximum.
Yeah, absolutely.
So this means that the cost plus seems better than the other.
Yeah, so cost plus performs very well here. Like you say, it can very sensibly mitigate the risks, and it's kind of helps with competitiveness. But the problem is that this spider plot up here shows the acceptability to industry. Industry would be very happy with the cost plus mechanism because all of their costs are reimbursed by government. But it doesn't perform very well down here, which is on the criteria around acceptability to government. So the government doesn't really appreciate this mechanism because it doesn't allow the costs to be passed on to consumers. The government and taxpayer has to bear those costs, and because it does not promote efficiency, so it doesn't give the industrial company any incentive to reduce costs over time because all of the costs are reimbursed by government, for example. So this is where you see some models performing very well from an industry perspective, whereas other models performing better from
How do you combine these two different pieces of information then?
So broadly, we discussed them at a workshop with a number of public sector and private sector stakeholders. So you can really understand if there are certain things that are deal breakers for one or other from one or other perspective. So For example, if one of these things, the inability to transition this model to a market-based mechanism, for example, was a deal breaker for the government because they need essentially an exit route from subsidies. Whereas for the private sector, for example, CCS certificates that are tradable didn't address any of their cost uncertainties and didn't provide a strong enough revenue incentive or investable enough model. So that was ruled out on this basis that for early projects it wasn't going to be financeable. So you can find some deal breakers, and then on the rest you can create for example, a weighted average score where you combine all the criteria together and see which performs best overall.
Okay, thank you very much. Any quick question from the audience? If not, thank you very much to Antonia and Amelia for this very nice presentation. So we can move to the next presenter, Dr. Engelmann, which will talk about perception of CO2-based fuels and their production in international comparison.
Yes, can you hear me?
Yes, I can hear you, and I can see the presentation.
See the slides? All right.
Yes.
Thanks for the introduction. No PhD yet, but still my way. I like the sound of it, so thanks. Welcome everybody. Thanks for joining this presentation on the topic of perception of CO2-based fuels and their production in international comparison. My name is Linda Engelmann. I work at the Chair of Communication Science at IWCCU Aachen University, and together with my colleagues, I'm investigating acceptance of sustainable technologies. Let me shortly introduce the project I'm working on, which is Ccu, which you probably heard more about this morning in the presentation by the coordinator Jose Serra. The aim of this Horizon 2020 project is to set up a technology that enables us to produce hydrocarbons by using water, steam, and renewable electricity. The produced hydrocarbons will then serve as a component for synthetic jet fuels, and this way more energy can be stored per processed CO2 molecule, and a reduction in greenhouse gas emissions per jet fuel ton can be achieved. As a social scientist, I'm no expert on technological details, so if you're interested in more input on the technology, feel free to visit the project's website or perhaps reach out to Jose Serra. Yes, what I'm going to talk about today is the societal acceptance and of the technology and the Ccu end product. Before I'm showing you some hands-on results on societal acceptance, let me shortly give you an idea of our work approach, why and how we are integrating technology acceptance in a project like Ccu. Different from other, perhaps more typical acceptance studies in which acceptance is considered at the end of a technology development, we consider it right from the very beginning of the developmental process due to some advantages. For example, perceptions of customers or other stakeholders can be used to inform technical designers in early phases about acceptance barriers, and where this is possible, degrees of freedom of a technology can then be used once they are identified in the early phases of development. Secondly, first efforts to educate the public and to raise awareness can be made. And lastly, information and communication strategies can be specifically adapted to customer needs throughout the development of technology so that they are already existing once the product is ready for rollout. But what exactly is acceptance? How do we define it? Best case would be that the public likes a product and adopts and actively uses it. That's not always the case, since it's also possible that people haven't made their minds up yet. They are then indifferent and their behavior is ambivalent. That means it's possible that they make up their minds and perceive the new technology to be useful, or they go on to adopt a negative stance, leading to them rejecting a technology and ultimately resisting. And this resistance is the opposite of acceptance and can manifest itself in active forms of refusal, like, for example, local protests against new facilities or product boycotts, for example, combined with social media campaigns or something like that. And the research that has been previously done on the acceptance of CO2-based jet fuels is close to not yet existing. But when we look at CCS and CCU technologies in general, we see the necessity that also in the case of this technology, the investigation of perception and acceptance should be carried out. Because previous research found, for example, that in case of CCS, people's potential to protest against a CCS project was significantly influenced by the perceptions of risk and benefits of capturing carbon and storing it. Or for mattresses that are produced using captured CO2 as material, these were linked to perceived risks for health and the environment, and this gives us a hint about which underlying motives or perceptions can have an influence on an attitude, and that perceptions can be directed to different things, such as a technology or a product. And therefore we split the technology, so to say, since there are several objects of investigation that are possibly relevant. Since CO2 from industrial facilities need to be captured, in some cases a stream purification is necessary, and since it has to be transported, infrastructure is one aspect that can be evaluated, as well as the production process or steps that can take place. Apart from that, we have the final end product that has to be investigated regarding its acceptance, since a process and its product aren't necessarily evaluated equally, which becomes clear when you, I don't know, think, for example, about enjoying a well-cooked meal, but don't agree with the terms of living that animals in mass livestock farming have to go through. So there's always the possibility that you like the end product, but do not like the way of getting there, or the other way around. And to investigate these different objects, we use a mixed method approach of interviews as well as larger surveys. And we include, of course, technical experts, policymakers, and industrial stakeholders to get a deeper knowledge about possible rollout obstacles or requirements from a technical business case point of view. But we also prominently include lay people in our studies, since the public is an important stakeholder, especially when you think of recent movements in the course of climate change mitigation. And it's a group that can be studied using surveys, which makes quantifiable results possible. One recent study we conducted was an international survey on the Netherlands, in the Netherlands, Spain, Norway, and Germany, with a final sample of 2,187 people. As you can see, the distribution for gender, for example, was quite balanced, which is due to our method of collecting data in a quota representative manner. That means for the demographic traits of age groups, gender, educational level, and region, we aimed to collect cases in line with actual national realities. And in this survey, we let people evaluate the production as well as the end product by dividing the process into accessible steps, each of which was explained to participants. I'm not going to go into much detail here regarding the mode of data collection, but feel free to ask me afterwards or get in contact. Now let's get to the results. First, we compared the individual production steps. After being given an explanation of the steps, the participants were shown this so-called semantic differential you see here, and had to indicate on a scale from 0 to 5 how they evaluate the respective step. In this graph, you see the mean values for each pair of opposites over the whole sample. And as you can see, the steps of separation, purification of CO2 if it is needed, transport, for example, via pipeline, and finally conversion with the Ccu reactor are perceived to be acceptable and useful. And when it comes to costs, people do think that every process step included is rather expensive than cheap, and also transport is evaluated more negatively than the rest, although, as you can see, still ranking in the upper half of the scale. When it comes to the final end product that is to be produced in this project's case, a similar picture emerges. After being told how a CO2-based fuel can be added or replace conventional kerosene, people evaluated the product using the same semantic differential as before. I also included the standard deviation here to give you an idea about the dispersion of answers given. And similar to the production process, the product is perceived to be acceptable and useful, as well as rather efficient and environmentally and health friendly, but at the same time, price is thought to be rather expensive. To gather deeper insights, we then checked to see if there are national differences. So as it turns out, the Norwegian participants evaluated CO2-based fuels the most negative, but still positively when we look at the total scale in all points except of price, followed by the Dutch, the Germans, and finally the Spanish participants. So as you can see, there are national differences when it comes to the effective evaluation of the end product, being in our case CO2-based jet fuels. Apart from this effective evaluation, we are interested in people's acceptance in form of their willingness to really use a product. As you can see for this first statement that people had to indicate their agreement for, the general support for CO2-based jet fuel was the highest in case of Spanish participants. The same applies for the next step, people's willingness to actually fly with a plane fueled with CO2-based fuels. Norwegian and Dutch participants in this case agree significantly, their agreement is significantly different from the midpoint of the scale, so they rather agree as well positively and would fly with such an airplane, but agree significantly less than the Norwegians and German participants. And lastly, when it comes to preferences, a similar picture emerges when people are asked if they would prefer a fuel based on CCU to conventional kerosene. Now we know there are national differences, but we want to dive deeper into these results and see if we can also explain or perhaps predict acceptance. I picked the two countries with the highest and lowest mean scores for the three statements you saw before to show you that there are also different predictors for the acceptance of a CCU-based product when comparing nationalities. Using a stepwise linear regression, I inserted a variable to predict, in this case, cognitive acceptance. It was conducted using several statements like the ones you saw in the previous slide, all measuring the same construct, which is in this case cognitive acceptance. Then I inserted a list of other factors that we surveyed. These are, for example, demographic ones like age or gender, but also, for example, a variable we use to measure perceived benefits or perceived barriers. So let's see what the results look like. I didn't include the statistics here, but indicated the power of each predictor with an arrow for the sake of clarity. In the case of Norwegian respondents, preference of CO2-based fuels accounted for the biggest impact on acceptance. This construct included statements that indicated that people would prefer the CCU alternative over conventional kerosene. It's followed by the perceived benefits of using CO2-based fuels. That means the more somebody prefers the CCU-based alternative over conventional fuel, and the more they perceive the use of said fuel alternative to be beneficial, the more likely they are to accept CO2-based fuels. Smaller positive contributions to the model come from the respondent characteristic of environmental awareness and the positive perception of CO2-based fuels as an end product. This factor includes people's perception of the fuel to be acceptable, efficient, harmless to humans and the environment, as well as its perceived usefulness. And lastly, one predictor had a negative impact. The more somebody perceives CO2-based fuels to be detrimental and to pose disadvantages, the less they are likely to accept it. So as you can see, this model explained 55.4% of total variance, which is a promising result for now, but indicates that there are more factors influencing acceptance that haven't been identified yet. When we compare this case to the Spanish one, we'll see that there are differences. Again, the preference for CO2-based fuel over conventional kerosene is the strongest predictor, together with, again, the perceived benefits, but this time the perception of the production step of separation also strongly predicts our target variable, which was acceptance. They are followed by the user factors of environmental awareness and age, which means the more environmentally aware or the older somebody is, the more likely they are to accept the product. And additionally, the positive perception of the conversion step itself also positively influenced the acceptance. When it comes to negatively affecting predictors, there are two that were included in the model. The more somebody thinks the transport of CO2 is risky, and the more they associate the usage of CO2-based fuels with potential barriers, the less likely they are to have a high level of acceptance. And with 63.3% of overall variances explained, this model includes more and also different factors than the one based on Norwegian respondents' answers. Comparing these two national cases illustrates that there are not only differences in how the technology and its product are evaluated by people, but also in what influences their acceptance of the CO2-based product, being, in our case, jet fuels. But why am I showing you all of this? As we've seen, the perception and acceptance, as well as the willingness to use CO2-based fuels by the general lay society, could be somewhat better. while they are of course not the direct users, because they are not the ones fueling or flying the plane, and the results so far do not indicate that there is a complete rejection, a positive perception and an expression of need by the public can be influential. And in order for acceptance and perception to be more positive and for people to form fact-based opinions, they have to be given information on the object of opinion. Since we want to inform them in the best way possible, we look at what influences acceptance, as I just showed you on the previous slides. If we now know that acceptance is influenced, for example, by the perception of benefits and barriers, these things should be brought more into the focus of information strategies so that possible benefits can be brought into awareness and misconceptions about disadvantages can be eliminated. However, we also see that national differences can exist. Of course, nationality is only a carrier variable. That means underlying factors such as cultural differences have an impact and need to be investigated, but it's not nationality itself. Nonetheless, it shows us that there are differences, and in addition to nationality, there are probably other groups that are identifiable and should be taken into account. For example, we know that in technology adoption, there are distinguishable groups like early adopters that can bring their individual communicative and informative needs. And what we attempt to do is to identify these groups in the data in order to develop group-specific communication strategies. We have to ask ourselves, what does somebody who is either already open or opposed to sustainable technologies need to be informed about? And also, how do we reach these groups? What channels do they use to inform themselves? What has to be included in the messages and which level of complexity is best? And also, who should be the messenger? Who's the most trustworthy in the eyes of different groups? Apart from additional studies on the technology and product acceptance, will be in the future investigating these questions. All of them need to be answered so that we are able to conclude a useful information strategy to inform the general public according to their needs, and in this way pave the way for the rollout of the production and use of CO2-based fuels in a society with well-informed stakeholder groups. Yes, and that's it from my side. If there are any questions, I'd be happy to answer them.
Thank you very much for the presentation and being on time. So any questions from the audience? Hi, Arun. You have to type the question in the chat.
I'm going to upload the slides later, so if there are then any questions, just let me know, write me an email, something like that.
Hi, Arun, you are now a presenter, so you can speak to speed up the process.
Okay, can you hear me now?
Yes.
All right, okay. I have to apologize if my question sounds a little bit naive, so please forgive me. I mean, if I were a member of the public and I was asked the question, would you prefer to use a fuel which uses CO2, which would be otherwise released into the atmosphere and harm you and cause environmental warming, as compared to what is being done? I mean, it would be a no-brainer.
I understand your way of thinking, yes, but
so, but yet you find that when you go through the procedures, that's not the case. I mean, it's not always 100% support.
Yes, because we have to understand that lay people sometimes form their opinion on based on other things. For example, they don't understand that CO2-based fuel and conventional kerosene have the same, they are chemically seen like nearly the same, but in their opinion, perhaps they think, okay, perhaps this is a safety risk, or I don't know, the plane will crash. I don't, you know? So these are aspects that need to be investigated, and then these misconceptions can be eliminated so that hopefully everybody thinks it's a no-brainer to use them.
So basically what you think is they're worried about the fuel being different or being more hazardous?
For example, yes.
Okay. And also I was a little bit, I don't know, I mean, you showed some results, which showed some national differences. Can we really make too much of this? I mean, couldn't it be, I mean, I didn't see very large differences.
You think they didn't seem large, or they seemed large?
But I mean, did they look to you as being large, the differences in the
they were statistically significant, so they are existent. We have to find out what they are emerging from. As I said, it's not nationality itself, but for example, in Norway, CCS, CCU may be a different topic than it is to Dutch people, and that has to be brought into the formation of communication strategies when there is pre-existing knowledge in one country and not so much in the other one. So we can work with that, with these national differences.
Okay, one more question.
Mm-hmm.
I really think one of the toughest jobs is getting public opinion, to get people to spend their time to complete surveys. Mm-hmm. I mean, I'm always amazed how people are successful in doing this, because whenever I'm approached, it's, I have to be honest, it's I always put it back of the queue. So
yeah, we're happy that they take part.
So what's the trick? Because you seem to have quite a 2,000 sample for each study, or was it 2,000 people overall?
It's still 2,000 people, and we do that with the help of market research, for example. Some of our studies are in our personal background, or when it's smaller samples, but larger ones are done by using market research companies. Yes.
Okay, so it's people actually contacting. Sorry, Gianpaolo, if I'm stop me if I'm just.
Yes, we have to move to the next speaker.
Right. So. Okay. Sorry. We'll move on. So. Okay.
So thank you very much, Arun. Thank you very much, Linda, for the presentation. Now we can move to the last but not least presenter, which comes from the Realize project, and I will talk about social studies. Dr. Dunphy, the floor is yours. I hope doctor is correct, but it's what in the presentation.
It is correct, yes. Can you see my slides?
Yes, now I see.
Very good. Okay, so I'm going to be speaking on a somewhat related topic, and it's the human and societal dimensions of large infrastructure, whether it be energy or whether it be carbon storage and so forth. So my name is Niall Dunphy. I'm from University College Cork in Ireland, where I lead a group which is focused on the intersection of social sciences with science and engineering. And our research focus is on the human and societal dimensions of sustainability. So just a small overview of the Realize project, which was introduced this morning. Its full name is Demonstrating a Refinedly Adapted Cluster Integrated Strategy to Enable Full Chain CCUS implementation. And really what it's doing is working to develop a means to capture up to 90% of carbon dioxide from the various multiple small sources in operating refineries. So it's a Horizon 2020 project led by SINTEF, and we commenced last May. The coordinator will be giving a talk on the technical dimensions of this project tomorrow in session 3B, I believe. So achieving the decarbonization of Europe is a key goal of the European Green Deal. And we're probably sick of hearing that. But this required energy and industrial transition will both necessitate and will result in substantial societal transformation. And citizens have a crucial role to play in this transition, indirectly by accepting, supporting or resisting changes, and thereby influence other policy actors, or directly by giving their consent or refusing their consent to various policy options in democratic decision-making processes. So very often citizens are just perceived as a barrier. They're perceived as a group to be convinced, to be informed, to be educated. But in reality, they hold a lot of power in our democratic societies. That needs to be taken into account. So obviously the technical and the geological aspects of a carbon capture and storage project are of course the primary focus of planning and implementation. However, the Realize project also recognises the importance of understanding and appreciating the social context of potential CCS projects. And within Realize, we have a specific package of work which is seeking to develop an in-depth understanding of the societal, socio-political, and commercial contexts of carbon capture and storage and deployment. So this is a quick overview of the work package that I mentioned. It comprises 6 tasks. The first of which is a critical review of education and public engagement programs. What went right, what went wrong, what could be improved, what's transferable to other cases. The second is a task where we will develop an education and public engagement program for one of our case study sites and trial it with local communities. Third task then is a socio-political context analysis, where we will explore the socio-political lessons learned from various projects around the globe. Task 4.4 involves industrial context analysis, where we are engaging with key actors through an industry club. 4.5 involves public outreach activities, lifelong learning, where we aim to contribute to improve societal readiness through outreach and education programs. And finally, the last task then is synthesizing the various outcomes and results from these various tasks. The task that I want to talk about today really is the first one, which is a review of education and public engagement programs, and I'll touch a little bit on the second one, which will be the deployment of a new EPE program. So this task, and I'll be focusing on, comprises a critical review of education and public engagement activities associated with large energy and related infrastructure. It's intended that this work will contribute towards the development of a framework for social acceptance for deploying CCS at an industrial site. The examples, we identified key examples of education and public engagement through literature research and via partners networks using a snowballing approach. So we characterise 7 case studies of education and public engagement through a comprehensive desk study coupled with the use of targeted informants. In this respect, actually, COVID-19 came in quite handy because many informants were more readily available to speak with us and to spend time, to share their expertise and their experience with us. So you can see the 7 projects that we looked at in depth, some of which are CCS projects, others are other large-scale projects. The resulting report details the case studies, outlines the methods that they adopted for their education and public engagement programs. It explores key challenges, presents best practices, and it identifies what can be transferred, what can be learned from the various studies undertaken. So the deployment of the major infrastructure needed to realise the required energy in industrial transition can only be successful with social acceptance. Now this means acceptance by the public generally of the technology, of the type that the previous speaker was talking about, but also in the case of these large-scale projects. Critically, it also includes acceptance by the community which will play host to the infrastructure. However, the strong public opposition faced by many projects, whether it be in the energy domain, with CCS, or other related infrastructure, threatens to significantly slow down this transition. The term social acceptance, with respect to infrastructure deployment, it often implies, whether by design or otherwise, a passive acquiescence of a decision that has already been made. Such activities are usually concerned more with advocacy, about persuading people to accept. We know best. In the words of one of the questioners earlier, it's a no-brainer. You should know this. You should accept this, rather than involving these citizens into the decision-making or into the decision-making process. This is the so-called DAD model: decide, announce, defend. And unfortunately, it often becomes DADA: decide, announce, defend, and abandon, because there's no social acceptance. So what we talk about and we try to emphasize is social acceptability. And in the context of a project, it's the project itself that has social acceptability. It's inbuilt into it. It infers an effort to design and implement a project to be more agreeable to social stakeholders. It suggests and arguably requires a more participatory approach. The involvement of stakeholders, and particularly social and societal stakeholders, at a far earlier stage than otherwise would be the case. There is an implied acknowledgement of societal stakeholders' legitimacy. There's a provision for them to be involved earlier, and an understanding that they would provide real input into decision making. So perceptions of fairness play a crucial role in determining the social acceptability of infrastructure projects. And we can look at 3 dimensions of this. There's procedural justice, the way in which a process is structured and implemented. Is the process seen as fair? Is it implemented the way it should be implemented? Distributional justice, how the benefits and ills of a project are distributed. Are all the benefits of the project going to outsiders, and yet the local community has to deal with all the burdens? Is there a share in the benefits? And then the third leg of this is recognition justice. It's acknowledgement of the legitimacy of these social actors to be stakeholders in the project, that they have a voice. It's recognition of that role, as opposed to misrecognition. And we often hear terms like NIMBYism thrown around. And that type of disrespect often leads to tension between those who are proposing a project and those who may be going to be hosts of it. So it's important that each of these is included in any form of engagement program. So these are the lessons that we undertook, and they will be available in our deliverable from the project, which will be in our website in due course. I suppose one key lesson is you cannot engage too early. Early and open channel of communication with the public helps to build mutual trust between the communities and the process leaders. This reinforces the notion that the project benefits when stakeholders across all groups are involved in the process. Ideally, the local community should be involved in the process of location selection, permitting, policy making as soon as the project is proposed. And often this is quite a challenge to those promoting the project to understand that local communities do have advice, do have opinions, and that those opinions do have to be taken into account, not necessarily accepted, but need to be taken into account in the decision-making process. There's great value in having staff who are liaising with the communities. It's useful to hire staff who already have good relations with local communities, or those who have the skills to developing trusting relationships with communities. Very often when we're dealing with infrastructure projects, it's an engineer with lots of technical knowledge who's thrown into the fray and expected to communicate the project to a local community. And very often these people do not have the skills to interact with the community in a way that's needed. Also, having somebody who is a known entity in the community, or at least with some members of the community, is vital in building trust. Having these community liaisons can ensure that issues can be dealt with promptly and preempt any challenges, any problems. There's an advantage to having a blended learning, or having a blended approach to communication. Official communication, formal communication is very useful, but also having informal channels can be useful to ensure effective outreach and build trust with communities. And this I suppose is what Dwyer and Bidwell describe as building a train of trust between the developers and local stakeholders. They know that they're being listened to. First impressions count, and no more so than when you're talking about infrastructure development. You build trust through early, open, and responsive communication with communities. Actions by a developer are interpreted through the relationship. A poor relationship could lead to actions to be seen as hostile. A hands-off approach might lead to perceptions of the developer having something to hide. So it's very important to build that first impression, build a good relationship early on. The provision of good quality information is key. It builds trust, it preempts issues, but it needs to be tailored to communities. It needs to be tailored to the community. Effective and trusted communications promotes the credibility of both the project itself and indeed of the developer. And as I said, it's important to develop an understanding of a target audience so that you can implement a tailored communication strategy which reflects the cultural and other specificities that apply. And this is key, and this is something that is often overlooked in these type of engagements, is that listening is also part of communication. In fact, it may well be the most important part. So educating and informing can help improve understanding on particular issues, but on its own is a very limited strategy, and it minimizes the value of the process. Real engagement means that you have a two-way flow of information. It encourages the public to voice their views and interests to inform decisions. So again, very often in these type of engagements, we think it's all about educating, informing the public. But we too, as developers, can learn a lot from the public. Local knowledge is very important. So the next steps, what we're doing in this program, is that we're going to build on our developed knowledge of the EP programs. And we're going to develop an education and public engagement program, which will be co-designed with community stakeholders from a case study in the Cork Harbour area in Ireland. We're going to take an intersectional approach to this. This will consider socio-demographic aspects of the community, such as gender, life stage, economic privilege, and so forth. And then we're going to trial key elements of this education and public engagement program to evaluate their effectiveness, to identify areas of potential improvement, and to determine what's transferable, what's useful for other approaches. That's the end of my presentation.
Thank you very much. Very nice presentation.
If there's any questions, happy to take them. If anyone is still awake at this time of the evening.
They are certainly awake and they are willing to ask questions. So now you are moving to the task 4.2 and 4.3 of the project, right? So
that's right, yes.
You set the base with this very interesting analysis, because some of the outcomes were certainly very interesting. Then moving to the try to apply what you found in the 4.1 and see whether it works. If I can say so.
Yeah, I didn't catch that. Giampaolo, was there a question? Sorry.
I mean, now that you had some insights or some understanding from the analysis in task 4.1, now you are trying to apply these findings to the Cork area to see how they react.
That's exactly it. Okay. Yeah. So we're developing an education and public engagement plan that will be rolled out within the Cork area. Obviously, in the context of the current restrictions, that's an interesting proposition, but it's still going ahead, and we're still working on it.
You will do multiple approaches, or just to see how people react to the different approaches, or you're going just for one approach and see what's the final reaction?
The key thing is that we will actually work with the community to develop the approaches, so see what the community themselves want.
Okay.
Rather than test approaches, yeah.
Okay. Thank you very much.
You're welcome.
So if there are no further questions, we can close this session. Thank you all for attending. Thank you, the presenter, for the very nice presentations. And now you can move to the post sessions where there are the panelists waiting for you for the questions. Thank you very much, and hope you are enjoying the workshop and you enjoy the rest of the day. Bye.